As I said, I am organizing today's lecture in this way. I am providing a summary of what I did about rainfall runoff modeling so far, very brief summary, and I am providing this summary because I want to take the opportunity to correct a mistake that I made last time. I noticed by looking back at the videos that I overlooked the one relationship that I need to correct, not a big change. After the summary, I want to browse with you the PowerPoint that you can download from my site, because as you may remember, I didn't have the opportunity to browse the PowerPoint presentation last week. I want to tell you which slides are important and which slides you can forget, because there are slides that I didn't deal with in my lecture. So I want to tell you what are the important slides and what are the slides that you can forget about. And then I will go on, I will turn off the PC, and I will go on with two more rainfall runoff models. So let me summarize what I did so far. We are talking about rainfall runoff modeling. You remember that this is an important topic for us because it allows us to understand water resources availability by simulating river flow data depending on meteorological data like rainfall, temperature, etc. I started to deal with this topic by providing a very simple example, which is the time area method. I started from the rational formula and then I explained to you the time area method. Fine. Then, after dealing with the time area method, I came to this formula, which I'm writing again, for the computation of the river discharge accordingly to the time area method. The first form of the relationship was a summation. And I wrote something like, if I will remember, let me check what I have written. It was Qn, I expressed Qn as a summation from k equal 1 to n of I n minus k plus 1 times area k. This was the summation that I have written. This is correct. Okay, you can find it in your notes. But then I passed from the summation to the integral, and I wrote something like Qt equal to the integral from 0 to t star of, I said, I tau dA over d tau times d tau. I think this is what I have written. Let me check if it is exactly what I have written. Yes. I put here dA tau. Okay? This is what I have written. This is not correct because it's not I tau, but I t minus tau. Because if you look at the summation, you see that we start from n and we subtract the index. N, when passing to the integral, it's represented by tau star. So I have to write here, sorry, tau star minus the index of the summation, which is the variable of integration now, the integration variable. So this is the correct way of writing it. Okay, I wanted to make this correction because, and you can notice, if you look at my slides, that it's correctly written in this way, maybe with different symbols, but the meaning is the same. So you can notice my mistake, my previous mistake, if you look at the slides. Okay, so this is the change that I wanted to make. Good. So this was the first example of rainfall runoff model that we dealt with, and then I said, if you want to pass to more complex models, I need to increase the number of equations, because usually more complex models mean that I don't have to model, I don't have just one unknown variable, which is river flow, but I have more unknowns, because I am including more variables to model, like the height of the water table, or more state variables. And I said that I may need to introduce state variables if I want to make the model structure more complex. And then I said I need more equations. And then I wanted to make clear what are the kind of equations that I can use. And therefore, I introduced the concept that conservation of mass and conservation of energy and momentum are always satisfied in fluid mechanics, which is relevant for us because hydrology is the study of movement of fluids, water. So fluid mechanics is very relevant to hydrology. And then I said I can use conservation of mass, which I already used here. With the time area method I used the conservation of mass. Maybe implicitly, but it's clear that I'm applying a conservation of mass principle. Now, if I want to make the model more complex, I need to introduce additional balance equations. For instance, for energy and momentum. And then, to summarize, to finish my summary, I introduced the Reynolds transport theorem because I said that all these balance equations of mass, energy, and momentum can be derived through the Reynolds transport theorem. I introduced the concept of control volume, which is the volume to which these conservation laws are applied, and I said that the total variation in time of an arbitrary extensive quantity n, which can be mass, can be energy, can be momentum. An extensive quantity is a quantity that depends on the volume. So I said that the total variation in time of any extensive quantity can be written as the integral extended to the control volume of the product rho times eta, partial derivative, sorry, in dB plus the integral extended to the control surface of, again, rho times eta, which multiplies the vector of the fluid velocity times the versor to the area dA inward versor, okay, the versor directed inside the control volume. Now, I want to say something more about this theorem. This is basically a relationship that is applied in 3 dimensions because in this case, for instance, velocity is a 3-dimensional vector, the versor is a 3-dimensional vector, and therefore the quantity rho and eta, remember, eta is mass density of the fluid, and rho is mass density of the fluid, and eta is the concentration per unit mass of the extensive property. This quantity vary depending on x, y, and z. So vary depending on 3 dimensions. To apply this theorem is not easy, because you need an integration over 3 dimensions. We will not deal with the derivation of our balance equation from the Reynolds theorem. We will not prove how to derive, for instance, the mass balance equation that we use in Reinforanoff modeling, how to derive it starting from the Reynolds theorem. It would be too complicated. I don't want to do it. I'm just mentioning the Reynolds theorem because I want you to know that conservation of mass in fluid mechanics, conservation of energy, and conservation of momentum can be derived starting from the Reynolds transport theorem. I just want you to know this. And if you ask me, should I remember by memory the Reynolds transport theorem, I would say Basically not. If you are really interested in getting the loud, maybe I appreciate if you remember. It's one relationship which I think is useful to remember because it helps you to understand how this transport, this balance equation work, but it's not really needed. What is needed is that you remember that the basis for this balance equation is Reynolds transport theorem. This is needed because if you want also to study with more details and you get a textbook written in English, you will find that they start from the Reynolds transport theorem. So I don't want that you are missing this important piece of information. I think it's important that you know that we start from it. But then I will skip the proof and I will provide the balance equation to you in the final form, which is very, very much understandable from a physical point of view. You will see, like in the time area method, you have seen that conservation of mass is very easy to understand in practice. What we do is very easy. We assume that rainfall that falls over a given area simply transfers the basin to outlet. It's very easy to understand. Okay. Now, at this point, let me go through the PowerPoint. So afterwards, I can turn the PC off and move forward with other models. Tomorrow we have lectures from 11 to 1 p.m. starting at 11 in room 0.5. Is downstairs in the old building. Okay. And tomorrow morning we will deal with theory. In the afternoon, if you have a notebook, please bring it. And before you leave the room, let me, because I recommended to install a software, just stop by 1 minute and I summarize, okay? And I tell you. Okay, so let's see this, if it works. Let me check. Just 1 second. And let me browse this. Okay, so we have here an introductory slide which is self-explaining. So even in this case, this slide you already know it, so I don't need to. This is not really. I didn't use this slide, so you can skip it, no problem. Even if it's not complicated, so I'm not sure. Okay, try, please try. But okay, a bit better. And this slide states that we can apply conservation laws and in particular mass, energy and momentum. This explains that we can apply these conservation laws at the basin scale, or we can decide to divide the catchment in subunits. I mentioned to you this possibility. This is Reynolds transport theorem. No need to spend time on this. I just want to mention that we have 3 terms at the right-hand side here, because I mentioned to you that in this case the formulation is more general. They allow the control volume to move with its own velocity. You can skip the 3rd term because it's just something that we don't use in hydrology. We usually assume that our control volume is the catchment, which is fixed. We don't consider catchment moving in time. This is an example of what is a catchment. That is our control volume. We usually refer to the catchment. We can decide to subdivide it in subunits, but at the end, our overall control volume is the catchment. Some models apply the conservation laws at the catchment scale. Some models apply the conservation laws at the scale of a given subunit. I mentioned this possibility. So far, we dealt with the time area method. It is applied at the catchment scale because we divide the catchment in sub-areas, but this subdivision is just finalized to understand the shape of the hydrograph. It's not a subdivision dictated by the need to apply the conservation law at a lower scale. We apply the conservation of mass with the time area method at the catchment scale. Okay, this is a slide that explains that watershed can have different size and forms. This is a very important concept because our problem is relevant because to understand how a catchment reacts to rainfall is a very complicated issue. And it's not yet clear what determines the shape of the hydrograph. For sure, the form of the catchment is important, but we notice that very similar catchment with very similar climates react in very different ways to rainfall. So we are still trying to understand what determines the reaction of the catchment to rainfall. And this is important for both floods and droughts. Of course, people are trying to understand what is the impact of geology, not just the shape of the hydrograph, the external geometry, but also the internal geometry, including geology, because of course different geologies mean different geometry for the subsurface flow paths. So you have water flowing underground, and of course the ways the water flows underground are different depending on geology. Many other things, but the moral of the story is that for many reasons, for the large part, what determines the shape of the hydrograph is still unknown to us. Here there is, I don't understand if I am making mistakes myself or...
It's the same problem because last week also was like this.
We shut down every 10 minutes.
Okay.
And they could not solve it. Because this was the analog device.
Okay, the next one, anyway, believed to me was not relevant, but still. Okay, it's coming back. Every 10 minutes, you say, and there is no way to...
No, they will bring a new projector and put it here.
A new projector, really?
Last time it was like this.
Okay, so let me go back. This is not relevant. It explains how to determine the shape of the catchment by following the catchment divide. And here you have a general scheme that explains how rainfall runoff model works. They try to mimic the reality. You see, you have reality in the upper scheme, and the virtual reality here below. And this is reality. This is virtual reality. So this is just a scheme that explains how we want to emulate the real system. And this is just an explanation that the hydrograph, the shape of the hydrograph is determined by different factors, several factors. Some of them are not completely understood, as I said. So this is just to emphasize the concept that we still do not know many of the reasons for the shape of the hydrograph. The hydrograph, I remind you, the hydrograph is the graph of river flow depending on time. Okay. And here it's a general consideration that I already mentioned to you. What are the inputs and what is the output? And here there is something that I didn't mention to you. I want just to say a few words. We have several types of rainfall and off models. We just started to deal with them by giving just one example. I will provide more examples later on, but the concept that I want to emphasize is that we have several different models available. Basically, the choice between one model or another is dictated by the purpose of the analysis and data availability. So you have to first have clear what you want to do. What is the variable that you want to simulate? What would you like to obtain? And then, depending on the purposes of the analysis, you have the literature suggesting different models. And in the following examples that I will show to you, I will explain what are the differences, what are the advantages of each model and the limitations. Okay? So knowing the models, the available models, their advantages and limitations, depending on the purpose of the analysis, on your target, you decide what is the best model. And also, you will know what are the data requirements of each model, so which data you need, and then basing on data availability, you select the model. For instance, if you have a model that needs the topography of the catchment as input, you will use it only if you have this information, of course. Okay? Now, model structure. You can distinguish between lumped model, lumped means applied at the catchment scale, versus spatially distributed. Spatially distributed means that you subdivide the catchment in subunits. Okay? So in this case, lumped model, the conservation laws, again, are applied at the catchment scale. In this case, you apply the conservation law to each subunits, and then you have to sum up the contribution of each subunit to the formation of the river flow. Of course, these spatially distributed models are more computational intensive, because I mentioned to you that you may have like 30,000 of subunits to which you have to apply your conservation equations. And I want to emphasize that spatially distributed models need much more information, because for each subunit you have to define the behaviors, the area of the subunit, in many cases the soil type, in many cases the land cover, and preferably the precipitation in each subunit. So you can't give, if you use a spatially distributed model, just one value of precipitation over the catchment at each time step. You would need, in principle, to give precipitation over each unit, because of course, if you want to compute the balance equation, mass balance equation, you need to know rainfall on your subunit. If it's not available, you can assume that rainfall is uniform over the basin, but of course it's an approximation. This was my fault really, and there was written black box versus conceptual versus physically based. I can go on here. What does it mean? Black box, conceptual, physically based. Let me start from the simpler concept. Physically based. What does it mean? It means that model equations are based on the concept of physics, like conservation of mass, conservation of momentum, conservation of energy. These are physically based equations. They are based on the laws of physics. And of course, I mentioned to you this opportunity that we have. But you can also use empirical equations. And we will see an example. You are aware that it exists a physically based equation that you may apply. But if it is too complicated, like to compute the mass balance is too complicated, then you can use a conceptual equation, which is an empirical equation. Conceptual. We will see an example where we substitute a physically based equation with an empirical equation. If you are using empirical equation, your model is not called physically based, but it's called conceptual. Based on the concept. A third solution is black box. And you use a black box equation. What does it mean, black box? Means that you are using again an empirical equation, again, not physically based, but this empirical equation has nothing to do with the concept that you want to emulate. Has nothing to do with physics. So let me better distinguish between conceptual and black box, because both are empirical. Both. Physically based means you are applying the laws of physics. With conceptual and black box, they are both empirical, with one important difference. In the conceptual case, your empirical equation tries to emulate the physics. So you are still using the concept. It's an empirical equation, but it's similar, an approximation of the physical equation. So you are still using the concept. With the black box equation, your empirical equation has nothing to do with the physics. So you pass from the physics to an empirical equation emulating the concept, to an empirical equation that has nothing to do with the concept, but may work better. In some cases, black box equation work better than physical equation. And you may wonder why. The reason is simple, because when you have a lot of uncertainty, then a physically based equation may be not a good idea to use. Now, all these equations contain parameters. What are the parameters? What are? You can read here that a parameter is a constant or variable term in these equations. In this equation, no matter if they are physically based or conceptual or black box, in any case you have parameters. Let me clarify what is a typical parameter in a physically based equation so you can get the meaning. The roughness coefficient, coefficiente di scabrezza in Italian, which is used to model the water flow in rivers, is a parameter. A parameter that is plugged in a physically based equation. The parameter can be a constant or can be variable in time. Is something that appears in these equations, and if you change the parameter, you change the shape of the equation but not the structure. Let me be more clear. Let's suppose that you express your river flow with a black box equation, like Qt is equal to a constant C that multiplies rainfall at the same time. Okay? You can do that. You can model river flow as a function of rainfall at the same times through a very simple equation like this. Maybe it works. You can try it. In this case, if you change the value of C, of course you change the shape of the hydrograph, but you are not changing the structure of the equation. The equation is still a linear equation, linear, that connects river flow to rainfall through just one parameter C. And again, if you change C, you change the shape of the hydrograph, so you change the shape of the relationship, but do not change its structure. And what is the added value that parameters give to you? Of course, it's flexibility. It's the opportunity to adapt your hydrograph to the real catchment behavior, the real catchment functioning. So parameters are a very relevant opportunity for us, because by changing the value of the parameters, we can calibrate the model. We can find the value of the parameter that brings the model to work best. These parameters are always included even in physically based equation, and I mentioned roughness. Okay? I just move because I don't want PC or projector sleeping. Okay, so parameters are a very important component of rainfall runoff model. An important concept, parameters need to be, we say in technical language, calibrated. Means that, as I said, you have to find the optimal values for parameters. The values that provide the best performances for the model. And the procedure to find the best values for the parameters is called calibration, or optimization, or parameterization. These are synonyms. Let's skip the concept of validation. I just want to anticipate that you know, when you calibrate the parameters, you have to check that the values are indeed good values for the parameters themselves. You have to check the parameter values. Because you calibrate the parameter by optimizing model performances, we will see how to do, but then we have to check that the parameter values are indeed good. And we will see in the exercises how to calibrate and validate models. For now, just keep in mind that you need to calibrate the parameters to find the optimal values, and then you have to check that these parameters are indeed, these values for the parameters are indeed good. Okay? Now, these are general considerations, and which also highlight the importance of time scale. Depending on the time scale you are working with, meaning what does it mean time scale? Means the time interval to which you want to simulate the river flows. Do you need hourly data? Do you need daily or monthly data? These are very different situations. Depending on time scale, you need different models. Basically, just keep in mind that the shorter the time scale, the more difficult the problem becomes. So if you work with short time scale, you get more problems, more complicated problems. It's quite understandable because you want to increase the level of detail of the simulation. So of course the model becomes more complicated. Rational formula, we already spoke about it. So you have the slide supporting the time of concentration, that's fine. And these are formulas for the computation of the time of concentration. We just mentioned Giandotti's formula, so you don't need this slide. And there are other formulas just for your information. And again, formula for time of concentration. This is the time area method. You already know everything about it. In this case, you can skip this. You can skip this slide. because I don't want to go into the detail of the time area method. I put the slide just for your information. And these slides, there are some of them, clarify the shape of the hydrograph for different, the hydrograph as given by the time area method for different shapes of the watershed. So in this case, you see that this is a rectangular watershed which has for each equal values for each sub-area between the isolines. And then if you have a uniform rainfall, you get this hydrograph. But again, you don't need to study this in detail. You see a triangular watershed that gives in output of the time area method this kind of hydrograph shape. Again, this is for this shape of the watershed. I don't know how to see rhombo in English. You get this shape of the hydrograph. Again, these are details I'm not interested in. And you see more complicated shapes. You get, of course, more complicated hydrographs. And now I'm starting with the second example, which is the linear reservoir method, which you already know. But I think it's important that I dedicate some time on it. Now, let me be clear. I can just, I think I can turn the PC off. Hopefully. Now, let me clarify what I am doing now. I am introducing a second example of a rainfall runoff model, which is different with respect to the time area method, but it's a kind of model that you already know because you took already an hydrology course. But I want to mention it because it serves to me to introduce a third example that I will probably introduce tomorrow, which is a more complicated model. And therefore I need to deal in detail with the two basic models, which are the time area and the linear reservoir. These are